In this video, we're going to discuss covariance structures. This is what we need to consider when we're doing a mixed analysis of variance. So we're going to look at our vision data, the longitudinal vision data in this case, and ID subjects are measured for multiple visits. There are in this data set anywhere from 1 to 7 visits. They're labeled 0 for the baseline and then 1 and so forth, up to 6 additional visits after baseline. So when we do a mixed model and we want to take into account visits, we need to add in under subjects the ID, and under repeated measures, because we're measuring the same subject more than once, visits. And the mixed model will estimate different covariance structures. In other words, there's visits may be correlated with each other, or they may not be, but the degree of correlation is an estimate, and that takes some parameters to use. And so we're going to consider a number of different models that are here. We're going to let's start with the identity matrix. Now, IBM has been kind enough to give us a little handout on all these, and these are all their structures, covariance structures. We're going to start with identity. And I point out this is matrix multiplication. There's a variance over here. So if you multiply out this matrix, you're going to get a 4x4 matrix with variances in the center. Now, this is just their stock model. We have in our example 7 visits. So we would have 7 columns by 7 rows. And the diagonal is basically, it's variance 1 by variance 1, 2, 2, 3, 3, and 4, 4, and 5, 5, and so forth. In this particular, so we have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7 corresponding to visits. And this type of matrix only applies to the within subject variable. In other words, we're talking visits here. If we were talking about whether the person is going to become myopic, emmetropic, or hyperopic, those 3 things are between subjects, because you either become myopic or hyperopic. You don't become both. So that's a between subjects variable, and it is not subject to this particular type of estimation. This is strictly the repeated measures or within subjects kind of variances that we're concerned about. As a reminder, when we look at these are variances, the covariance, so this would be the variability between visit 1 and visit 2, visit 1 and visit 3, visit 1 and visit 4, and so forth. What is the relationship? In this particular model of covariance, we're saying that that correlation is 0. So this structure has constant variance. There is assumed to be no correlation between any of the elements. So it's all this sigma right here. It's all that squared, all that variance, and no relationship between them. So let's see what that gives us. Come here. We have the dependent variable. We're going to look at refractive error as a function of visit. We're not going to look at anything else other than visit. On our fixed, we have our visit in here for our model. Under statistics, we're going to test for our covariance parameter. Now that test is just against 0. We're going to look at our means and we're going to see what the change is over time with means. We're going to compare them. We're doing an unadjusted test. That's what you can adjust, do different kinds of things, make a Bonferroni adjustment or something if you'd like. Continue. Okay. And we get this structure. We look here, there is only one parameter that we have to worry about in terms of our repeated effects. So there's only the one variance. That's what that's talking about. There are 6 visits, so they have, for each of those means, it's n7 minus 1, or 6. Then we have an intercept term, and we have a total of 8 parameters that we're estimating. Number of subjects, 1,272. And we can look down here at the means. We'll come back to this later, but in general, across the entire sample, which includes myopes, emmetropes, and hyperopes, we start up here and we steadily go down as people go in the direction of myopia. All right, let's look, and here is our estimate of the variance. It's 1.3. So we have just this one measure, we get 1.3. Another thing we want to look at is this information criteria. Now, this by itself doesn't mean too much. This number, 22,519, is really big, but it's not, it's as it stands by itself, it doesn't mean anything. 22,521 means that you can see how close those are. They're 3 points apart. We have only 1 degree of freedom, so estimating that hurts a little bit, but not much. So what this does is it adjusts for the numbers of parameters that are used. And it's not a big difference here, but we'll see that it is a little bit bigger in some of the other types of models. All right, so here we have a single variance and no covariance. What else could we have? In our mixed model, linear, scaled identity, let's look at diagonal. Actually, we should go through this route. So diagonal, why pick diagonal? Diagonal, this is diagonal. Now notice we still have 0 relationship between our visits. But now instead of just one overall variance, there's no little variance sign over here. Instead of just one variance, notice the subscripts are different. So we have 1, 2, 3, 4 different variances that are going to be estimated here. And when we look at ours, there's also a 5, 6, and 7. But there's no correlations. We're still not going to estimate a correlation. We're going to say that correlation is 0. We're fixing it 0, and we're just looking at this. And so what do we get? First of all, we can look at our Aki-Ike. It's now 22,000. Before, it was 22,521. Now, it's 22,056. So we have gained about 500 points. So this one has a few more parameters that it's estimating. It fits a little bit better, and we're winning on that better fit. Because even though we have more parameters, this number 22,056 is smaller than the 22,521. And since the number's so high at 22,000, I mean, 500 points is pretty good, but it's not a huge proportion given this. So we improved a little. We did not improve a whole lot. So what other kinds of things? Oh, if we look, our means are actually the same as they were before. Whoops, that's the one before. So 840, 612, 840, 612. And the estimate of the variance, now instead of just the 1, like was up here, we have 7 variances that are accounted, 0 plus 1 through 6. And these are the variances for each one. And you can see as refractive error increases, or goes down actually, so does the variability. As the myopes and emmetropes begin to diverge from each other, the variance is going to be going up. So we can control for a lot of this variance if we just added future refractory status. But the interesting thing is the means are the same. All we're doing with this within subject modeling is we're improving, we're making our standard error a little bit better. See here it's 0.024, 027. They're all kind of different. If we look up here, they're all the same. Well, I guess they change a little bit because sample size is changing. So the estimates are a little different. We don't have as many with 5 and 6 visits as we do with, say, 0. All right, let's look at another one. Let's try compound symmetry. And let's see what that's all about. So here we have compound symmetry. And you can notice that there is this overall sigma squared plus this little additional sigma squared, which the sigma of that is used to represent the correlation between the covariances. Now let's look at this. They're all at the variances all have the same number. When we were talking about diagonal, we had subscript 1, 2, 3, and 4. The variances were different, but then we had 0 for covariances. So the covariances weren't related to each other. Now we say they're related to each other, and they're related in an equal way. So the correlation between visit, this is visit 1 and 2, 1 and 3, 1 and 4, 2 and 4, 3 and 4, all those visits are correlated the same. Remember, our table goes out to 5, 6, and 7, but we're just looking at these first 4. And it's the same way down there. So now our structure has constant variance and constant covariance. So if we look at this model, there's 2 parameters that we're going to estimate in this case. The last time there were 7 because there were 7 different variances. This time there's only 2 because we have 1 here and then this sigma 1 is estimated. Let's see how that guy does. Okay, our structure is compound symmetry. Here's our 2 estimates. We're now down to 13,731. Remember before, when we had the that's the wrong thing. Okay, I have the wrong, where are we here? Information criteria. Here we have our diagonal. We had 7 parameters because we had 7 variances that were different, but there weren't any covariances. Here we have 2 because we have this central diagonal plus the sigma 1, which was the covariances. And we're down to 13,731. That is a big improvement. Oops, I seem to have that in twice. Big improvement over the diagonal, which is 22,000. And our means are still the same. Our covariance structure, now we have these 2. So this is that overall sigma, and this is the sigma 1. And that's the one that, I think actually I said that wrong. I think this is the sigma 1, the diagonal offset. That's the variance estimate right there. All right. Let's try another one. Analyze. Mixed linear. So an interesting thing about visits is you would expect that visit 1 would be correlated with visit 2 more than it would be correlated with visit 3. And visit 1 and 3 would be greater than visit 1 and 4. But you might say that, okay, they're correlated differently, but the further away you get, it's kind of a constant correlation. So it's more correlation the closer you are, but it's a constant type of variance, and that's AR1, autoregressive correlation. Now let's see what that looks like in our little diagram here. So now we're saying we have this constant variance. Here's our little sigma squared going out there. We have constant variance, but there's also a constant correlation in here, but it is multiplied. So we take this variance, when we multiply, it's going to be sigma squared rho here. So if it was, let's say, a correlation of 0.8 or 0.7, let's say, this would be 0.7 times the sigma. This would be 0.7 square, about 0.5 times the sigma. And this would be cubed, so about 0.25 times the sigma. So the variance gets smaller as you get further away from the original. So this is basically only has to estimate 2 parameters. It's estimating this parameter and the correlation parameter. And the correlation between any 2 elements is equal. It just says what I just said. So the correlation is going down the further, or the covariance is reducing the further away you get. Let's see what that looks like. Now we were at 13,000 back here, 13,700. We did a little better by considering that correlation. We're now down to 11,000. So that's pretty good. Again, our means are all the same. We don't change means, just standard error. And here are those 2 correlations. So we have that sigma squared, that general one, and then this is the rho that's multiplied times that, and squared and cubed. And in our case, also raised to a 4th, 5th, and 7th power. All right. Let's try maybe one more. is bring it home a little bit more. So what we did before, let's come here first. We have now we could go to AR heterogeneous. So before we just had this one sigma squared. Well, we could make everybody different with this relationship here. And let's go ahead and do that one maybe. AR1 heterogeneous. Let's see if that buys us anything. Notice that little pause, it took a little bit longer. Our repeated effects, now we have 8 parameters. We added a few there. But we look at our Ake and it's 10,800. Now, we went from 2 parameters to 8 parameters, but we didn't really gain all that much. We went to 10,800 before we were at 11,000. So we gained about 200 points, which is it's a gain, but it's not very much considering how much more we had to add parameters. And down here we can see our estimate is getting to be a little bit more complicated. But these are the variances for each of the visits, and they get a little bigger as it goes down. So we add a little bit of the diagonal advantage, but mostly we added to the covariance advantage to get down, but it isn't really using different estimates each time isn't buying us all that much. Okay, one more. And let's look at it on here. Let's go to unstructured. Now, unstructured is basically saying everybody has its own thing. So there's a separate variance. The subscripts are different for the diagonal. So visit 1 variance, visit 2 variance, visit 3 variance, visit 4 variance, 5, 6, 7 are all different. The covariance of 1 and 2, 1 and 3, 1 and 4, all different. So we are measuring all these different variances. 1, 2, 3, 4 times 4 is 16. Let's try that and see where it gets us. And it's thinking a minute on this one. There we go. And that says 28. Only got 16. It's coming up with oh, that's because it was 16 and that but we have 7 visits, so it's a little bit more. It's half. So 7 times 7 is 49. Half of that, it's actually not quite half. But anyway, it's 28. That's a lot more. When we got down to 10,009. Now, that is better. But actually, it's 800 better. It's an improvement. We may want to do it, but it's a little bit more complicated. So that's covariance structures. Now, the when you're deciding what the best fit model is, you start with that Ake criterion and you pick the smallest one. But you also want to consider the nature of the model and the structure, and you want to make sure it makes some sense, that it is a logical relationship. You have a reason. Like we had the reason of the AR models because they it only makes sense that there is a gap. Now, whether or not everybody has to be different is another question. So you might want to go with a simpler model that may not be quite as good a fit, but you definitely want to do a model that's reasonable. So those first ones where it only looked at the difference in variance, or it said everybody was exactly the same and there was no correlation between visits, that just didn't make sense. So here we have a better fitting model, and it's a good one to add on. So that's covariance structure.